In this video, we are going to be discussing reflections of electromagnetic waves on a conducting surface. So, reflections on a conducting surface. Okay, because in previous lectures we had talked about what happens when electromagnetic waves hit an interface and then they're transmitted through, but there is this kind of attenuation where the electromagnetic wave is dampened out. But now we're going to also consider the reflection aspect of it. So what we're going to do is we're going to start with the boundary conditions. So these are your standard boundary conditions that we've used in previous lectures, where the first one is that the perpendicular component of the electric field at the boundary basically equals the free charge density on it. So here I am talking about one is one medium, let's say the one on the left, where the incident wave comes from. Two is the medium on the other side of the interface, and where the wave would be transmitted. The second boundary condition is the perpendicular component of the magnetic field, and in that case, they're basically the same on both sides of the interface. The third boundary condition is the parallel component of the electric field, and in that case they're equal to each other on either side of the boundary. So we're essentially talking about this side over here where the electric field components are. And then the fourth boundary condition is the parallel components of the magnetic field. And in that case, what we would have is the difference in these components would be responsible for any charge, any current density that we have on the interface. And here N is the direction of the propagation of the wave. So anyway, so I'm sorry, N is the area vector for the interface. It's basically the one perpendicular to the interface, and I already said that sigma is the charge density and K is the current density. Okay, so now let's put some conditions on this. So let's say that the media are linear. So we can make an assumption about the connection between the epsilons and the mu's, and we're also going to say that the medium N1 is non-conducting, and the other medium N2 is conducting. So it's basically something like light coming in from air, that's medium 1, incident on a metal like, I don't know, silver, on medium 2 on the other. So it's almost like we're building a mirror. We're also going to assume that these are monochromatic plane waves, and that the wave is traveling in the z direction. So it's going to be monochromatic plane waves traveling in the z direction. Okay, and we're going to polarize in the x direction. So okay, so now we have all that information, we can now write out our waves. So for the electric field, this is a complex wave. The incident wave is the amplitude times e to the I k1z minus omega t in the x direction. The incident B field is 1 over the velocity in medium 1, E initial, or incident I should say, e to the I k1z minus omega t in the y direction, since this is a doubly transverse wave. The reflected wave is some amplitude e to the I minus k1. So we're going to consider z to be just a positive number. Minus 1 over v1. So the reflected wave is now pointing, there's been a phase change. It's now pointing in the opposite direction because we've polarized things in the x direction. So really that minus sign goes on the y hat. And then the transmitted wave if we write it out, notice that K2, so it's the wave number for the second medium, and this is going to be in the x direction. And from our previous study of the electric field and magnetic field in a conductive medium, this wave number is complex. So I'm going to put a little tilde on top of K2. And finally, the magnetic field is K2 tilde over omega. That's the velocity part of it. Okay. Okay, so now we've got all of our waves written out, all the different components. And now what we're going to do is we're going to apply this specific case of polarization in the x direction, propagation in the z direction to our boundary conditions. So now we can kind of simplify our boundary conditions again by saying that there is no perpendicular component to the electric field. It's in the x direction, so it's basically in the interface. And the same thing is true for the magnetic field. So essentially what we have is the wave coming in, and we now have this interface where we have the electric and magnetic fields basically in the plane of the interface. Okay, so that means the only you have to care about is the parallel components to the interface. And so that means that our amplitude for the incident plus our amplitude for the reflected is equal to that of the transmitted. And since there is no, let's see, from the first boundary condition, if there is no perpendicular component, then that's going to imply that there is no free charge on the surface, which means there's no free current, which means that if I write this now in terms of electric fields instead of magnetic fields, what I get is 1 over mu1 v1, the difference in the electric fields for the incident and reflected, minus k2 tilde, mu2 omega, the amplitude of the transmitted wave. Okay, so now we have basically these two boundary conditions. We can put them together and combine them. So I'm going to take boundary condition 4 and rewrite it as the difference in the incident and the reflected electric fields. And then that gives me a mu1 v1 over mu2 omega k2 tilde, the amplitude of the transmitted wave. And now, if I was to take this equation here and add it to this equation right here, then what I would get is I would drop out the reflected part, and I would get two times the incident amplitude is equal to 1 plus mu1 v1 over mu2 omega k tilde 2, all of that times the transmitted amplitude. And if I call that beta tilde, so beta tilde is mu1 v1 over mu2 omega k2 tilde. Now beta is a tilde because the k2 is a complex number, so beta now is a complex number. But if I put that in, then what do I get? I get 2 times the incident amplitude is 1 plus beta tilde. Or we get a form which looks similar to what we saw before in terms of the scattering of waves. 2 divided by 1 plus some constant factor times the incident amplitude. Like so. So it looks exactly like the previous case, except for now we're dealing with a complex factor beta. We could now take that, plug it back in, and solve for the reflected wave's amplitude. And what you would get is 1 minus beta tilde over 1 plus beta tilde times the incident amplitude. Okay, so now we have solved for the specific cases, or the case for what is the amplitude going to be of the transmitted wave and the reflected wave, and in terms of these different constants. So I could think of now a specific case, and that is, what if I have a perfect conductor and with perfect conductor, then the conductivity is infinite, k2 tilde is infinite, beta tilde is infinite, and that means that my reflective is minus infinity over infinity times the incident. So I have minus the incident amplitude, which means that the transmitted amplitude is 0. It is a perfect mirror.